Hello and welcome back to Calculus 1 section 2.5, limits at infinity. Now this is going to be reversed from infinite limits. Now we are looking for the limit when x goes to positive or negative infinity, and the answer will either be a finite number L or positive negative infinity. So we are looking for limits at infinity, and two different concepts you learned in pre-calculus 1 would fit within this definition. Before we do the application, let's take a look at some basic examples. We can start talking about limit as x goes to infinity for 1 over x. What do we get as you look at your graph for 1 over x? So what do we get as x goes to positive infinity? 0. Very good. So as x goes to positive infinity, which is this way, positive infinity, the y value diminishes down towards 0. Yes. Another example. Limit of x goes to positive infinity for x squared. Positive infinity, very good. Limit as x goes to negative infinity for e to the x. Zero, very good. Because to go to negative infinity on x, you are going to the left to infinity, and you see that the y value diminishes down to 0. Limit x goes to infinity for inverse tangent of x. And you're probably going, why? Because Calc 2 and differential equations are coming up, right? You know how winter was coming for a very long time? You never got there? So now the Calculus 2 is coming. So the inverse tangent, it's one of the very important functions because we are going to have derivatives and integrals involving inverse tangent, not so much inverse sine or inverse cosine, inverse tangent in particular, which is why I'm asking the limit question. It's going to pop up in your DFQ class. It's going to pop up a few times in Calc 2. You need to know inverse tangent graph. It's going to have these boundaries at negative pi over 2 and pi over 2, and it's going to snake through like this. And now you're looking at the graph and you're going to tell me the limit of inverse tangent as x goes to positive infinity. Pi over 2. Then I am going to ask limit as x goes to negative infinity for inverse tangent. Negative pi over 2. I'm going to ask for the limit x goes to 0 for inverse tangent of x. 0. Good. Now that's right, just the point in there and the origin. Great. So these are your limits at infinity. And as you can see, in some cases, right, you are getting infinities. In some cases, you are getting numbers. And the lecture is over. Now we do application. What is this good for? Right? Why bother? You don't have to define something in mathematics and just leave it there. Right? It's good for something, whether it's, physics or whatever. So what do we get to define using limits at infinity? Well, the common sense to complement the previous lecture, it should be what? Horizontal asymptote, exactly. Remember how you had to memorize those rules when the exponents are less and larger, and then there is the asymptote here? Remember that? Good, because you don't need it. Now we're going to learn the limit definition for it. So you don't even have to review that stuff, all right? Horizontal asymptote, ha. Definition. Ha is a horizontal line. Well, actually, I skipped the word again. Ha of f of x is a horizontal line, and you can have multiple, right? Remember that we had two horizontal lines for inverse tangent. So it's not only one, could be multiple. So horizontal asymptote of f of x is a horizontal line at y equals L. It's a horizontal line, so equation is y equals a number, where limit x goes to positive or negative infinity of f of x is equal to L. That's it. You don't have three cases, like you don't have three different cases and then either one of them. You just have this one. And now we can find the horizontal asymptote for f of x equals 1 over x. You will just say limit x goes to, and then you pick whether you want the positive infinity or negative infinity. So you would say goes to infinity, 1 over x equals to 0, implies horizontal asymptote at y equals 0, which is the x-axis. And you know that your 1 over x follows x-axis, right, as it approaches from both. Now, there are certain problems, say, you want to check for horizontal asymptote for f of x equals 3x squared plus 1 divided by x squared minus x plus 2. So let's say you are interested in horizontal asymptote. So what do? Well, you have to take the limit of this function as x goes to, let's say, positive or negative infinity. Okay, sounds good. Let's see what we can do. There is a very specific method to solve what we call rational functions, which is when you divide polynomial by polynomial. So this one works in these cases. So what do? I divide with the highest exponent present in the problem. In this case, x squared is the highest exponent. So does anyone know what the horizontal...
Oh, it's like the coefficient is right. 3 is bigger than...
Negative 1.
3 is bigger than...
So I have 0, I have negative 1. Any other takers?
I remember that is the denominator.
3.
3?
No, denominator would be the vertical asymptote, right?
No.
Denominator.
The numerator.
Okay, so we have 0, negative 1, and 3. Obviously can't have all of them. So what? Should we take it outside or settle it in here? All right, so when you have a polynomial divided by polynomial, we are going to divide every single, we have 5 separate terms. You will divide each one by the highest exponent you have, which is x squared. So you will divide everywhere by x squared. So here we go. Limit x goes to infinity, and now you have to go 3x squared divided by x squared plus 1 over x squared. Now you have x squared divided by x squared minus x over x squared plus 2 over x squared. And now you cancel everything you can. So this is the method to do this when you have polynomials. This is 3 plus 1 over x squared divided by 1 minus 1 over x plus 2 over x squared. And now my question, now remember the rules, we learned the limit laws. You get to apply a limit to each one of these individually. So you have a limit of 3, then you have the limit of 1 over x squared, and each one individually, right? What would be the limit x goes to infinity of 1 over x squared, right? So technically you are dividing, you are dividing 1 by infinity. What is 1 divided by infinity? Goes to 0. There is a very simple explanation for that. Here is the, what is this? Calculus1 lab, who cares? Not important. I have a piece of paper here which is going to represent 1, number 1 paper. If I want to divide this by 2, I would have 1/2, and then, right, when I divide by 2, 1 divided by 2 is 1/2. If I divide by 4, I would have 1/4. See, the 1/4 is smaller than 1/2, 1/2 is smaller than 1. The larger the number that I divide by, if I divide by 8, the result is this big, right? Remember, I'm not going to rip it. This is where we started, right? When it was 1 divided by 1. And now, 1 divided by 8 is this big. 1 divided by 16, 1 divided by 32. There are 32 of these pieces that fit in a 1 full piece of paper, right? 32 of these. 8 this way, or whatever way they fit, right, on the piece of paper, right? So 32 pieces. The larger the denominator, the overall fraction is smaller. So clearly, when you divide by infinity, your 1 paper, you are cutting it infinitely many times. So, gone. Which is why limit of x goes to infinity, when you have x in denominator and whatever number, you can put 10 million if you want. If you cut infinitely many times, you would get 0. That's how all of those people in sports go bankrupt, right? They have millions upon millions upon millions of dollars, and then you just divide that by infinity, spending, and it's just bankrupt after a few years, right? Was that Tyson, right? What, $30 million? How? Started a space program or something? I don't know. Anyway, so each one of these would go to 0, because when you divide a number by infinity, it just goes out. And you just have 3 divided by 1 is 3. So, ha at y equals 3. Please remember to give me the proper mathematical equation. Horizontal lines, y equals a number. So we have horizontal asymptote at y equals 3 in this case. So that's the story on horizontal asymptotes. I believe, let me just kill this puppy. You win, okay, fine. Did not sound good.
A question.
Yes.
You said we can look at that and tell that what the asymptote is. Is it because someone knew about the redundant?
Yes. The reason why, no. The reason why I asked that is because in pre-calculus you memorize 3 rules because you don't get the limit definition. So you can't do the limit, right? I made a joke, do you remember? And most of the people said no, and I said good, because you don't need it. So if you remember from pre-calculus the rules, then the rule in pre-calculus said that if you have the same order of exponents, like I have a square and a square, then the horizontal asymptote is when you divide front coefficients, 3 divided by 1, which is exactly what we eventually got, 3 divided by 1. So that was the rule you memorize, one of the 3 rules you memorize in pre-calc, but now you can retire all of that because you have the limit definition, right? You know that your horizontal asymptote is obtained by calculating the limit at infinity. So you don't need to memorize any of those rules. Clearly, if you know them, you just get to skip doing the limit, so you are faster with solving certain problems. But it's not necessary for survival. It's necessary to remember the definition for survival because that one works all the time, right? One more example of these horizontal asymptotes and functions. Now they have this somewhat spicier case here. What is the limit as x goes to infinity? Lock the doors. Square root of 16x to the 4th plus 64x squared outside of the root plus x squared divided by 2x squared minus 4. This belongs on a shelf where you put mathematical gymnastics. This is it. No purpose whatsoever. It's just, look, Ma, what I can do. All right. What is the highest exponent to divide each term by? X squared. Good. Because the square root of x to the 4 is x squared. So it's x squared that is the one that we look. So now if you know that and you just look at the problem, you immediately know, right, that the answer is 5/2. But then we can also do the limit and we can compute. So when I divide everywhere by x squared, when I divide the square root by x squared, that x squared has to undergo square root and it will bump its power into a 4. Let me just clear that algebra because throughout the years I know that some people spontaneously combust here. X to the 6. Square root of x to the 6. So what is the square root of x to the 6? X to the 3rd, right? Now, if I need to, for whatever reason, let's say I have x third and then I have cube root of 5. If I need to stuff this under, right? So if I'm taking the polynomial and I want to stuff it under the root, it will pick up the power and become square root of 5x to the 6. In algebra, 100% of your problems went this way. You want to simplify, 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 simplify. Well, in calculus, some of the problems would be backwards. You saw that, right? Factoring, right, Nicola said, factor the linear term. You never factored a linear term before. Well, now you learned you can. So this is what we are going to do now. Having this idea, I'm going to divide each one of these by x squared. So this one is getting x squared, this one is getting x squared, this one is getting, I sound like opera. This one is also getting its own x squared. And you get the humpback whale and you get the all right. And the tank with it too. So now we stuff the x squared under the root and it becomes x to the fourth. Plus x squared divided by x squared is 1. 2x squared divided by x squared is 2. Minus 4 over x squared. So this is our life. And now you also have to simplify under the radical. So limit x goes to infinity. These guys cancel. So you get the square root of 16 minus 64 over x squared minus 1 divided by 2 minus 4 over x squared. So now what do we learn? This is going to go to 0. This is going to go to 0. So what do you have? Square root of 16 minus 1 over 2. Oh no, plus 1. I know that the answer was 5 over 2. Square root of 16 is 4. Plus 1 over 2 is 5 halves. So, ha at y equals 5 halves. Horizontal asymptote for this function. So there was this one trick, right? When you are stuffing algebraic expressions inside the square root, they pick up the power. When you are taking them out, they are losing the power in terms of, exponents, right? So these are the little algebra tricks of the trade that need to happen, right, to do these calculations. Yes?
Why does it go to 0?
What? The 64 over x squared, or?
No. Why do they go to 0?
Because of the, remember what I showed with the paper? The bigger the number in the denominator, right? So if you have 64 papers, right? So think of a book that has 64 papers. That is a book with what? 128 pages, right? So you have a book of, let's say, 150 pages. If you take that book and you chop it up infinitely many times, there's no book, right? So I don't care what kind of a finite number I have in the numerator. If I'm dividing it by infinity, which is you're plugging x is infinity, right? So x squared, that's still infinity. When you square infinity, you get infinity. So when I divide a finite number a with infinity, it goes to 0, right? Because you are cutting something infinitely many times. If you divide it by 2, you have 2 halves. If you divide by 4, you have 4 quarters, right? So you are getting something. But if you are to sit there and forever chop it, right, to infinity, you get nothing out of it, right? Because it goes to 0. Because the half becomes a quarter, the quarter becomes an 8, the 8 becomes a 16th, and every time is smaller and smaller and smaller and smaller and smaller and smaller. So if you go to infinity in those cuts, you get a 0 at the end. So that's why each one of these goes to infinity. Like in the previous example, right? You had 3 of them to go to infinity. Because each one was dividing 1 divided by infinity, 2 divided by infinity. They all go to 0. Well, that was your first concept from pre-calculus explained through these limits at infinity. There's another one. So we had, the slant asymptote. Good thing you mentioned that. I didn't even consider it. Slant asymptote is a very rare creature that exists in only one case of a function, which is rational function where exponents are off by 1. So, and slant asymptote is not what I'm looking for, but now since you mentioned, let's talk about slant asymptote for a second. So guys, slant asymptote is going to be, I'll call it SA, and that's going to be mx plus b of some kind, because slant asymptote is going to be one of those angled straight lines. You do not need limits or any witchcraft that we did over here to compute that. All you need is a polynomial long division of polynomials. Hey, how are you? Come on in. No? So all we need is the long division of polynomials to calculate slant asymptote. So what is the way you get this? If you have, I understand this is calculus class, but sometimes, intermediate algebra is important. So if you have this situation, some kind of f of x, when you're dividing polynomial p of x by polynomial q of x, those are both polynomials, and what you are getting is that degree of p of x is by 1 larger than the degree of q of x. So situation would be like this. Say your function f of x is 3x to the 6th power minus 4x cubed plus x squared minus 9 divided by x to the 5 minus x to the 4th plus x minus 6. You see that the exponent on top degree is 6, on the bottom degree is 5, and you have to do long division and just do the first two terms in the long division, and you will get y equals mx plus b, which would be the slant asymptote. So for slant asymptote, we do not involve calculus in any shape or form. We have the infinite limit for vertical, limited infinity for horizontal, and the slant asymptote will always remain intermediate algebra, algebra 2, whatever you call it, long division of two polynomials. So now do long division to get sa. Okay, so that's that part. So what is the second one and the last concept for tonight for our limits at infinity? It's the concept from pre-calculus that you probably forgot, which is called end behavior of the function, right? So end behavior of the function. Now, what is the end behavior? End behavior is where you explain what is the end of the function, where is the end of the function going. Let me give you an example for very simple y equal x squared. If I draw the graph, I see that this end of the function is going to the left and up, and this end of the function is going to the right and up. And I can represent that with limits. I had that disguised, didn't talk about it at all, but I have it here. So the top line is your horizontal asymptotes, the bottom is your end behavior. Now I am going to give you the diagram of all four in one spot, so you don't have to break your head. Now I'm going to do this in red because this is technically the definition. There is no definition. There's just, oh, this is not a graph. This is just me dividing into four spaces. All right, so, well, actually it is a graph. So let's do it this way. So you might have a function go like this. You might have a function go like that. You might have a function go like this. You might have a function go like that. What are the mathematical limit formulas that describe each one of these four behaviors? Well, this one is limit x goes to positive infinity, because x goes to the right, of whatever function you have, and the y goes forever up. So positive infinity on x, positive infinity on y. You should be able to fill in the other three quickly, right? The one on the bottom, x goes to positive infinity because it goes to the right. What's happening with y? Negative infinity because it drops down. On the left side, top, limit x goes to negative infinity because now the arrow pushes towards left of the function, and the answer is positive infinity because it goes up. And finally, the last one is limit x goes to negative infinity of f of x is equal to negative infinity going down. These are important for your analysis of answers in differential equations. You are eventually going to run into the very first population model, which is exponential function, and then you are going to do the analysis of end behavior and conclude that that model on a large scale is garbage. I'm serious. Why are you laughing? Population at time t is initial population e to the kt. This is a population model you learn in pre-calculus. It will be revisited in Calculus 2. Finally, it will be beaten and replaced by good stuff in differential equations. What is the issue with this population model? Are we experiencing exponential growth in people and technically decrease in all other populations? Yes, right? But is it this way? No.
There's no carrying capacity built into the equation?
Exactly. There is no cap. Is this planet of infinite size? No. Now, what is the graph for exponential function in its pure form? It looks like this, right? So if you have your time axis and you have your population axis, what is the end behavior telling you on this end? On this end over here, it tells you that, right, we started from a 0, fine. But what is on the right-hand side? On the right-hand side, the end behavior tells you that the limit as time goes to infinity of the population function, you're going to have infinite population. No, you won't. We need to eat. We need a place to sit. We need the electricity to charge a cell phone, right? You cannot have any of those if the population is infinity. There is something that is called carrying capacity of the planet, which is calculated by approximating how many resources, farmable land, and other things we have. And scientists can't agree, is it a 10 billion or 15 billion people? But we're going to be there tomorrow, whatever number they pick. Because at the point, right, we don't live very well underwater. We don't live very well in any of the Arctic or Antarctica circles. We don't live very well in deserts. Sure, there are people that somehow survive in those conditions. But most of us will be dead in like 6 hours. So, well, okay, 6.5. So you can't have this as a population model. You have to use what we say logistics model, which introduces the carrying capacity, which in the limit would give you that carrying capacity as the highest population that the planet can sustain. And then moving to another planet doesn't solve the problem because exponential growth doubles population, let's say, instantly, right? What do you think, what's the population now, by the way, of the planet?
8 billion or something?
7.5 billion, right? 7.5 billion. What do you think population was 30 years ago?
Under 6.
30 years ago is what? 1990? Let me shock you. Oh, actually, no. I wanted 1980. Sorry, I wanted 40 years ago. That's in the lifespan. Your parents are that old, or about. Population in 1980. 4.4 billion. We have 7.5 billion. It's not roughly half, but yeah. The population on this planet roughly doubled in 50 years. So if you have exponential growth, then in 50 years, double it again, let's say. But no, the more people you have, even more people you have. You will have those problems as word problems in Calculus 2, when you will be calculating the derivative to calculate the change of the population as you go on. So wait for chapter 7, and you will have the word problems that deal with these things. Now, obviously, differential equations are going to do much better way, because calculus is going to use this joke of equation. Yes?
How do you calculate the people that die into that? Because there are people that die, there are diseases, there are famines.
Well, you don't actually, because this model kind of mushes all of that into one constant. There are predator-prey problems, there are for population. So you want to calculate the population of rabbits, let's say. Well, you have predators that eat rabbits, right? So the habitat where those rabbits are, the parameters, alpha and beta and so on. So there is delta parameter for death rate and alpha for birth rate and so on. So there are different parameters that you, in a more complex problems, and you do that in differential equations, which is why, of course, it's so important. In this case, when you have this equation, right, technically mushes everything into one, and it's not a good model. Now, if you want to watch the situation, you guys go to population clock, which is .gov, census.gov. So this is official government website, which gives you United States versus the world, and it shows the population. So we are at 7.6 billion. My information was, a few months old, so obviously I'm wrong. And top 10 populated countries in the world. 2 years ago, Mexico overtook Japan. Japan used to be the 10th most populous country, but then now they're experiencing huge drop in babies, which is really impacting their population. So you see that we are not even a quarter of where China is. They have 4 times, almost 5 times more people. And United States, right, is a third in the population. That number is going down, by the way, because of the prolonged, let's have babies later, and then figure out that you can't have babies later because now you're over 30. So, no, I'm serious. That's the issue that people don't talk about, but exists. So these are the things that you can observe. And there are very sophisticated mathematical models that calculate this, because no one is actually counting over there what's happening. But you can see the population growing, and this one accounts for all the deaths and all the births and everything, as much as the one in population over there for US. I don't have a closure for this. I'm just gonna shut